Yeah, this is a very honor and pleasure to be part of this forum. So a little bit of my background is I have a PhD in applied math and computer science, as was mentioned. So largely my interest has been in application of machine learning for multiple domains. So this is a collaboration with multiple researchers and scientists, and some of it is might actually give you some idea on what is the current trends that's happening in the field of agriculture. So yeah, the title of this topic is machine learning for precision agriculture, and especially especially phenotyping, how to accelerate for screening, right? So in the last many years, there's been a lot of effort on from the other side, right, where I come from, if you may, for genotyping and so the high throughput screening from that perspective, right? But the major bottlenecks is afterwards, So I just want a little bit touch upon that and give some perspective also from the Bayesian perspective on how we actually tackle these kind of problems, right? Next slide, please. Right. It will be, it'll be useful to mention that this is not a individual work. So a lot of my past collaborators have actually participated in ideas and, building this whole actually framework. So I'm really grateful for all of them. So really standing on top of these giants here. So especially Balaji, Chaitanyam, Sri Krishna, Parmita, Rita Gandhi, John Van Helmert, Shabri, Neil Hossman, Grant Richardson, Olaf Mueller, Harshit, Shiva Prasad Kumpatla, Tapan, and Arvind, right? So yeah, and a lot of these work is actually bits and pieces of collaboration with all of them. So where necessary, I will actually mention that pieces as well. Yeah, so going to the statement of the problem. Next slide. Yeah, just to give a little bit of background. So in agriculture itself, we are right now going through a lot of thought process on how to actually reimagine agriculture, right? So traditionally, if you're looking at any crop performance, agriculture crop performance, it's a function of very simply as G by E by M, and also there is a recent idea that a lot of commercial practices also is responsible for this. So that's one additional variability in determining the crop performance, right? So we know that for many years the yields have increased due to genetic improvement or better agronomy practices. So here G is the genotype of the crop that we're interested in, E is the environment, and M is the management practices. Right? While there is a sustained effort on increasing the yield, especially for many crops that we know of, like corn and wheat and others, soya, for example, there is also an equally increasing effort that's made in also reversing the diversity erosion that's happening in the many years. So how do we actually selectively breed to improve certain let's say vegetable crops which were earlier present but is slowly reaching a stage of extinction, right? While there is a lot of trends in actually the genetic selection process and the sequencing as well, but there is a gap actually between going from the genotype to the phenotype and for crop, especially for crop selection, right? So that's a bottleneck, right? And that's what we would like to address here. And yeah, and so that while the while the phenotyping methods and everything are something classically well known, both for crop modeling, which go as inputs, but the classical way is really manual and very time consuming. Next slide, please. That's where we'd like to bring in some innovation here, is that how can we actually open this bottleneck by accelerating this whole process. So in the past, we have worked on multiple platforms and sensors. So, be it, for example, in the ground sensors, where we are talking about water stress, right, measurement. How do we quantify for a particular germplasm that we are interested in? Can we actually put the sensors in the field and monitor them? And not like, the conventional way of doing this is actually going and installing instruments and then pulling it out and then going back to the lab, downloading it and everything, right? So can we accelerate that, right? And we are also seeing an enormous increase in the availability of consumer sensors, especially in the camera market, right? So both in terms of proximal sensing, drone-based images, and also satellite images, which are actually now becoming ubiquitous everywhere. So can we use these technologies in some way to accelerate this whole process? So that's the thought process in the whole of this. And while we are able to do this and this is done not at, this has to be done at multiple scales, right? So what we'd like to address this is, in this particular session, is much more how we are doing it from the machine learning perspective, especially where we take images collected from these different sources and how we can actually build generic models which can actually lead to quantification of the some characteristics. Let's say that the leaf area index, the biomass, or yield, all that can actually go into the existing crop models, and then we can use it for that particular variety selection, let's say for those particular biotic or abiotic stresses, or for particular performance like yield factors, right? Yeah, so that's a little bit of the context. Next slide, please. Right. So this is also even in the cameras, right? When we are talking about it, so these are not like RGB cameras as well. Within the laboratory settings, you can have like it's possible to take the multiple images from multiple modalities and integrate them together with either, like I mentioned, soil moisture sensors, temperature sensors, the ambient light conditions, measurement of humidity, the gravimetric and volumetric humidity in the soil, and then bring all of that into, it can all be automated, brought into the cloud, and then combining with, the genomic data can be actually improve the whole selection process. While these are the current trends, while it's possible to a limited extent, going from the lab, we wanted to also see and extrapolate this also for field conditions, right? And that's where the major challenge lies, because the lighting conditions, the background, the type of crop, all of this become variable parameters, right? So we actually want to go from specific conditions, specific cases to generic cases as well. So that's the whole objective here. Next slide, please. Okay, so often the question that is asked is that why not use some commercial platforms, right? So there are many commercial platforms that are available for actually phenotyping applications, while the context itself is very clear, but the major challenge in utilizing these are that they're very expensive, and it's very difficult to customize them, at least from our experience that we found. They require constant maintenance, and so for And not only that, for large field applications, it becomes challenging to take them out and then do remote monitoring. Right. So what we did is we built our own systems, and this is a joint work with Harshit. These days we get like Raspberry Pis, and along with that we can actually fit the cameras. And and what we've shown in the right side is a very simple system, and but this is specifically for lab-based phenotyping. But we have also seen some applications, and I'll show you a few applications where this could be also used in the field, especially in UAV images, right? So this is a work that had been recently submitted to PLOS One for its special paper on plant phenomics in precision agriculture, where we have provided more details on the setup and the architecture and how we capture these images, right? Although it looks like very small, but these, the camera itself is mounted, and what you see on the right side is it can be connected. Here it's all wired because we also have connected to a display system and powered with an electrical socket, but this can also run on battery pack, and it also can run wirelessly, right? So that it's once configured, it's actually pushing all the data to the cloud. Yeah, so this particular setup is especially used for destructive testing of leaf images. And in this particular case, our collaborator was interested in seeing if we could use, we could actually find out the largest leaf among the different leaf whorls that were available, and feed them. Once identified and exactly measured, those leaf areas could be fed into the existing crop models and for yield studies, right? Yeah. So next slide, please. Right. So when we look at this problem of machine learning, while it's always nice to look at these from complex models, and especially with the recent advent, which the previous speakers have also alluded to, I've always been a classical machine learning person. So the first thing to do is can we actually do this in a very simple classical computer vision way? Right. So that's the first question we asked ourselves. And, the Occam's razor principle, where, simplistic models should be preferred over complex models, and explainable models is preferable over black box models, So those are some of the reasons why we started actually working on and seeing if the images that we get, can we actually look at it from very simple machine learning models. Right. So what you see here is a very simple flow for what we worked on, in which the plant itself could be in the laboratory or in the field. So our system is kind of like agnostic to that over a period of time. But at the beginning, we took like specific cases under laboratory conditions. But after some time, we could also work under field conditions, right? And I'll talk a little bit about the challenges of that and how we actually overcame those in the future slides. So the classical way of looking at it really from the computer vision problem is like, once these images are pushed to the cloud, then you can just spin an instance and start processing as these images come in as well. So once these images are detected, and there is an instance which is automatically spinned, and they start processing in the background. So all of this can be very easily be automated on AWS, and I'm sure on other platforms as well. But the platform that we used is AWS. And one of the doing is change to look at it in the color space, right? Because these are color images, RGB images. So can we actually look at it from that space? Now, the interesting thing is, because these cameras are just off the shelf, we'd have to calibrate them for not only for resolution, but for quantification as well, right? And also for corrections. So one way in which we did is we took some, images. We took some images without the samples, and then and with the samples as well. And in both cases, the camera can be calibrated. So what you see is, we define a fixed area, let's say a calibration square, which can actually be used for, in this particular case, we were interested in measuring leaf area, right? So to measure a leaf area, to convert it from pixels to area, pixel square to area square, area dimensions, centimeter square in this case is what we are actually trying to map, right? So that's what we do. So, and in this particular case, we use the HSV space as mapping into the HSV space, and then we just are able to identify the calibration square, and then quantify the area that the pixels correspond to. Okay. The parallel stream that we do is converting the same images to LAB space, and then look at again from the thresholding perspective. You just look at the simple intensity, and then threshold them, and you can segment the foreground and the background. So this is the classical way of doing it. And then we are able to identify the leaf, multiple leaves, identify the largest leaf that we are interested in, excuse me, and then feed them into our crop model, right? So this is a very classical approach, and I'll tell you like what are the advantages of this is that it's very fast. There's only like one parameter to tune, but the restriction is that it's not able to handle diversity in the image samples, right, that we get. And the moment that we take it to the field, we face all kinds of problems. So we have tested this both for proximal images in Raspberry Pi and UAV, where we are interested in segmenting some images, and I'll show you some sample results in the future slides. So both has worked very well, right? But there are some cases where they don't, and I'll talk a little bit about that as well. Okay, next slide, please. Right, so what you see in the top image is a sample which was collected from the field, and this is the soya maturity, right? From the left to right is we see the growth phase clearly based on the color change. So since we are interested in the color space, right, the color change is, once it moves from green to yellow to brown, it becomes challenging. So this is a real scenario, and there are some ways of handling this. So the histogram earlier, which was bimodal distribution, is no longer just bimodal, right? So it's just spread across. So not only that, the image in the bottom that you see is from a rice field. This is also taken from literature to just show you the diversity of backgrounds that we have. The problem here is sometimes the background itself, let's say in the rice images, you have like, the weeds growing, or you have some moss growing, which also have green pixels, right? In this case, this is a real scenario where we encountered, which we encountered, and in which case no color-based segmentation no longer works, right? So that's when we thought about can we actually move from simplistic to models to changing them to make it more robust, right? And that means that provide it with a diverse data set and allow the system to learn from it. Now, that comes with, as the earlier speakers has alluded, that comes with some challenges, is that the ground for building machine learning models, generic machine learning models, there is a requirement for a lot of ground truth data. So one way in which we handle that is actually to use the earlier segmentation results now to feed into our machine learning model. So we already have the LAB and HSV segmentation. So can we use that as a ground truth rather than rather than just hand building these data set, because we are talking about really enormous number of images. And this is not just like, object detection or something that one has to go and make a pixel level segmentation, which is really, really challenging. What at the end of this, I would also like to mention is that all of our results have also been validated with an agronomist. So any moment that these earlier systems were failing, we especially started looking at them and understanding why they were failing, right? And I'll talk a little bit about that later. So the basic challenges which we are facing is, especially when we go to plots, is like the background is very variable. Sometimes there are tractor marks, the soil texture and the soil color varies, right? The plant itself that we're interested in, the foreground that we're interested in, is at different levels of maturity. And not only that, we are also sometimes we might actually see weeds which might be falsely captured as plant. Okay, next slide, please. So I have to give a little bit of perspective on also the and also how these algorithms are structured. So coming from much more from the Bayesian perspective. You can actually frame this as, these two slides are the only ones which have these equations, and I'll just keep it really basic. But the idea is that if you have the images X, where each pixel level is what you're interested in segmenting, which can be considered as X1, X2, and XP, right? And Y is the desired output, right? In this case, it's a foreground versus background. You could also have multiple. Also, you can have foreground, background, and let's say weeds, right, or something else. So this can be actually framed much more, in terms of intermediate layers, and this is Bayesian's perspective on neural networks. So what you see below is the FL is actually the is a function defined at each layer. Let's say you have capital L number of layers, and at each layer you have nj nodes, right? Sorry, NL nodes, and then each node has a corresponding weight and bias term, right? And there's also an activation function. So if the activation function is defined, then the problem actually of training reduces to finding the weights and the bias, right? So this is a very classical way of framing the deep learning problem from the Bayesian perspective, right? And actually, the whole problem of estimation of these parameters can be looked at it, that given the training data set, how can we actually estimate the parameters, the weights and the bias terms, right? Where the likelihood and prior terms are given, and maximizing this gives you the weight and the bias term. Here, D in the bottom, I've given it. That represents the training data set. And for once you train them, so you give the input data set and then obtain the weights and bias. So this is a very classical way of looking at the machine learning, deep learning, in terms of Bayesian perspective. Now, one interesting thing is that what has evolved is that the way that we frame the prior terms, right? So this is a regularization term which kind of like avoids overfitting the data, and it can be dropout or some form of L1 or L2 norms, right? Which kind of joins somewhere in our classical machine learning approaches of like ridge regression and yeah. Okay. So yeah, next slide, please. So when we come to the semantic segmentation, the current, popular approach is using the UNets, right? The UNet is, this is something that we also adopted, and this is a very intuitively easy thing to understand. simple thing to understand is that you just take the input image and encode it and then decode it to actually recreate the output segmentation map that we are interested in. Right. In our case, since this is just foreground background segmentation, so we're looking at in terms of the binary cross entropy loss optimization. Right? So if you just mention this again from the Bayesian perspective, if you just mention the encoding as E and the decoding aspect as D, then the whole problem can be formulated as give the the data set, the input images and the output segmentation Y. Can I actually build this framework right based on this loss function and the metric, to determine how we are performing. So this is also something very regular, but we made some modifications to this, and I'll also talk a little bit about that. So the mean IU is the metric that we use, right? I'd like to mention that most of these model building exercise was actually done on AWS with it's a very, the simplistic architecture. So we use the NVIDIA K80, and all of this was built using Keras. Okay, next slide, please. Okay, now to account for the fact that we have like multiple different variations from the field, we also did image augmentation. So there's only a limited number of data sets that we can get from the field, and field data collection and annotation is really, really challenging. So we started looking at both at laboratory conditions and also at field conditions. Can we actually augment them? So we did some simple full image augmentation and some extreme background augmentation, like hue, saturation changes, normalization, some adding of additive noise and things like that. So that definitely improved the risk. So I'll just probably share some results, and maybe if there are questions around this, then I can actually address regarding the architecture and the details later on. So this is based on the experimental setup that I showed earlier. So we did the calibration, the camera calibration, but once if you know the height and if you have some control point, so this is the red square that you see is equivalent to a control point, and in the field settings in the UAV conditions, we just have some GCPs to mark the heights, right? And then we can actually for this particular automatically identifying what's the largest leaf area. So, these destructive sampling is done in the lab and also in the field. Can we actually, take this both into the lab and into the field and identify the largest area? Okay, so what you see here is some preliminary results, and so the segmentation was done. So one thing which I would like to mention is that, at the beginning we used the color space, as I mentioned, as a basis to segment. And obviously, we had estimated and we had guessed that once you do a deep learning algorithm based on the ground truth built from color space, then it's going to segment based on color. It's also going to learn that, so that's something which we wanted to test also. And that's what happened as well in this particular case. So that's why you see in the segmentation results, some noise is also appearing, right? So because wherever there is shadow and where there is green color, there is, it starts thinking that it's a leaf, right? But you can actually identify the largest objects and kind of get done with that. But one way in which we changed this is like selected those images and rebuilt our ground truth data set, and now it's no longer based on color, but it's actually a full-fledged ground truth data set. It took us many hours to build that, but having a existing ground truth data to already kind of like accelerated the process, and it helped us in building up the data set. So we were able to identify the largest leaf area that we show here, and this is also being continuously verified by agronomists, and which actually feeds into the crop model, which I talked about earlier. Next slide, please. There are a few challenges, and then I'll conclude. So my main question always had been about interpretability and opening these black box models, right? So one thing which I mentioned is that sometimes, we want to understand what it has segmented. So we looked at some of the activation values, especially the last ones, and found that in certain cases, there were some artifacts which were getting produced. And these artifacts were because of aliasing, so we were able to correct them. And we did some perturbation analysis also on these black boxes and found that sometimes, the weights and everything were not getting segmented as you see in the right image, right? And this, then we started thinking, can we now augment our, the existing architecture using shape priors, so that's something which I'd like to conclude with. And that means it's no longer, identifying only like color based objects or continuous objects. Sometimes it's also continuous, not just color, but can you also look at other kinds of shapes, right? So my last slide, please. Yeah, so this is the discussions, and something to think about is these are some recent results. So these are not yet tested on images from the field, but these are some sample images from Cityscape, right, which is a very popular image data set. What you see on is actually a Hamburg driver view of the road. And what you see on the right side is a unit, classical unit, vanilla unit segmentation. We added some shape priors, into this. And by actually, I mentioned about priors, right, during vision analysis. So can we add some prior on the segmentation that we'd also like to do, so can we add those? So we added those. And we have very good comparatively better performance in compared to some recent models like the gated SCNN. But this is still work in progress. We don't have a full-fledged result, so that's why I've added it in the future work. So just to summarize, and I think I've just added some context regarding the how machine learning can help actually accelerate phenotyping, especially from lab and taking it to the field. And I didn't talk about satellite imagery, but that's also something that you could actually do, right, for large-scale application. The state-of-the-art segmentation, which is the most popular ones, they perform the coarsest segmentation, and our recent work has been to add some priors to also provide information regarding shapes, right? Can we add that rather than just looking at it from the hyperparameter perspective, but can you also do that, right? And these, quantification results can now be, are actually now feeding into some existing crop models, because the crop models can easily establish relationships between, let's say, the largest leaf area. LAI measurements becomes a little bit challenging, but you could derive it from the leaf measurements. The plant density, chlorophyll content, all of this is some things which can be quantified, right? Yeah, so I'll stop here with this current session that I wanted to present. Most of this work I've referenced, and I'll be now happy to take up questions.